Hi, and welcome to part 4 of lecture 36. In this last part, I just want to kind of give you an alternative point of view of what we're doing with the singular value decomposition theorem, which may kind of help kind of explain what we're doing and maybe why we would think that this is important. So let's just take, and we'll use R2 just to make life easy for ourselves. Let's say that we take an operator in R2, and we know from the singular value decomposition that there is a basis E1 and E2 and F1 and F2 for our orthonormal basis, or basis for V that's orthonormal, that allows us to write T using this property right here. Okay, so that gives us a different way of writing T. So let's think about what this map now does to the basis elements, right? What happens when we plug E1 into our function? Well, according to the formula, it has a singular value. We don't know what it is, but it doesn't matter. It takes E1 to the inner product of E1 with itself, and then it takes it to F1, and then it takes S2 or E1 to S2 times E1 E2 times F2. But now remember, the EIs are an orthonormal basis, so this term is 0 and this term is 1, so I get sent to S1 F1. And when we use these bases, so I'm taking this basis element and writing it in terms of the second basis element, we get something similar, right? We get S1 E2 gets sent to S1 times the inner product of E2 and E1, F1, plus S2, E2, E2, F2. This term vanishes. This term here becomes 1, so I'm left over with S2, F2. So think about kind of going back to chapter 3, we kind of learned that we can associate to any map, once you fix a basis, a matrix. So what happens when we take the E1s, the basis E's and the F's coming from the singular value decomposition? Well, notice what will happen is, right, so in general, when you write this matrix, right, you kind of label the columns by the original basis and you label the rows by the basis you're getting sent to. E1 gets sent to S1, 0. E2 gets sent to 0, S2. Right? So what you're getting is a diagonal matrix where on the diagonal matrix you're getting the singular values. Okay, so what happens here is another way of what to think about the singular value decomposition theorem is saying is that for any operator you can find an orthonormal basis, two different orthonormal bases, such that when you look at the matrix associated to these bases, okay, what you get is you get a diagonal matrix where you have the singular values. Okay, so these guys are the singular values. Okay. So a large part of what we've been doing, right, in this course is like given an operator is can you find a basis so that the associated matrix is, diagonal. Okay, so what the singular value decomposition theorem says is if you allow yourself the freedom to have one basis for V and another basis for V, then yes, you could actually always find a diagonal matrix that goes with it. And on that diagonal matrix are going to be the singular values. A lot of what we did in chapter 5 and chapter 6, was we kind of had one fixed basis. And then once you fix the basis, then we were saying, well, how well could you fill in the matrix? But if we allow ourselves the freedom of changing bases for V, you can actually always show that for any map, you get the singular values. You get a diagonal map or the singular values. So in fact, that's actually what we had over here, right? Is if we use this basis for the E's and this basis for we use this one basis for R2 and this other basis for R2, then this map here, with respect to these bases, will give us the diagonal matrix 2, 0, 3, 0. Okay, so we come to the end of all of our lectures, and remember way back in lecture 1, and it's actually like the first sentence in the textbook, where it says linear algebra is the study of linear maps on finite dimensional vector spaces. So if you made it this far, hopefully this sentence makes a lot more sense. We learned about vector spaces, we learned about finite dimensional vector spaces, and we've learned about linear maps, and we've been studying those over and over again. So the point is that the key result, key thing you need to know in linear algebra is linear maps. And to tie it into what we've done today is what the singular value decomposition is doing. It allows us to break apart any linear map provided you're in an inner product space into a particularly nice way. Okay, so that's it. There's no more. There's more stuff to look at in the textbook. There's a chapter on determinants. You may be thinking, like, what about determinants? There's a whole chapter on determinants that you might be interested in looking at. So that's chapter 10, if you have some time. And chapters 8 and 9, which we skipped, is kind of looking some more on operators on vector spaces that are either complex vector spaces or real vector spaces. So there's kind of some finicky stuff that you have to worry about whether you're looking over which type of operator, okay, and about how much further you can push some of those results. But at this point, you've learned enough. I know it's been a long semester, okay, you've made it to the end, okay, as the dinosaur says here, roar, but or otherwise goodbye. So I hope you got something out of it. I know online learning is not the best, and I hope you got something out of these lectures. I must admit that I'm kind of happy that this is the last lecture, and hopefully it's the last online lecture that I'll have to, per video, that I'll have to prepare. Hopefully I'll see some of you in person in the new school year, and I don't know when you're watching this, but if you're preparing for your final exams, good luck. I mean, just as a point of reference, today is the day before reading break, so it's pretty snowy outside today. So hopefully it's not too snowy for you today. Okay, that's it, and I'll see you in our online lectures.